In this video series, I'll demonstrate how to use ANSYS Fluent in Workbench design exploration to optimize the geometry of a nozzle. This part will show the parameterization in SpaceClaim, meshing procedure in ANSYS Meshing, and the simulation setup in Fluent. At this point, I've imported the nozzle's geometry into SpaceClaim and prepared a suitable enclosure. Then, to prepare for the design exploration later, I'll parameterize the desired dimensions. With SpaceClaim, this can be done without returning to the original CAD. Using the Pull tool, I'll select the radius of the barrel and under Groups, click Create Group. The parameter appears under a newly created Driving Dimensions folder, which I can rename Barrel Radius. I'll repeat this process for the radius of the exit and the radii of the entrainment holes. I'll use these three dimensions later to optimize the geometry of the nozzle. The geometry is now ready for meshing. I'll use edge sizing to control the size of the mesh elements on this edge near the impact of the nozzle stream and the nozzle tip. To do this, simply select the appropriate edge and then enter the desired size, 1 mm in this case. I'll also add face sizing on the impact wall of 5 mm. Now I can add some inflation layers to accurately resolve the flow in the boundary layer region. The interior walls of the nozzle and the impact surface will have fluid moving over them, so the inflation boundaries will be set here. In this case, it is easiest to select all the faces and then deselect the ones you don't need. Now I can generate the mesh. When I zoom in on the nozzle assembly, we can clearly see the inflation layers. The surface mesh is finer than the interior mesh by default. I'll insert a plane to view the interior mesh and confirm that the quality is sufficient. Before I set up the simulation, I'll add some name selections to the mesh. I'll add one for the inlet, one for the wall, one for the symmetry boundary, and one for the openings of the enclosure. These groups will be automatically passed to Fluent so I can quickly set up boundary conditions. Now I can close meshing and set up the fluid flow simulation in ANSYS Fluent. Firstly, I'm going to change the units for this case. I'll change pressure to PSI and temperature to Celsius. I'll be modeling the air as an ideal gas. To do this, I'll open the Create Edit Materials dialog box, and for density I'll choose Ideal Gas. The rest of the properties I'll leave at the defaults. I'll name it Air Ideal Gas. Clicking Change Create overrides the default setting of air. And I'll click Yes to accept. Next, I'll open the Viscous Model dialog box. I'll be using the realizable K-epsilon model with scalable wall functions. And I'll enable viscous heating because the fluid flow is compressible. Now I can add the appropriate boundary conditions. The name selections I added in meshing are present here, ready to be set. I'll set the inlet face of the nozzle as a pressure inlet and click Edit. The air will enter at a total pressure of 60 psi and a temperature of 25 degrees Celsius. The impact wall and symmetry boundary are automatically set, since I named them appropriately during meshing. The openings will be set as a pressure outlet with relative pressure of 0 psi. Setting the backflow pressure specification option to total pressure applies a specified value as a total pressure if the flow is entering through the face, and a static pressure if it is exiting. I'll set the backflow total temperature at this boundary to 25 degrees Celsius. Faces which were not assigned a name selection in meshing are assigned to this wall enclosure boundary, which applies a no-slip wall. We can check that it only contains the faces from the nozzle. For convenience, we'll rename this as Nozzle, since it includes all the nozzle faces. Moving to the Solver tab, I'll open the Solution Methods panel and choose Coupled for Scheme. I'll also enable pseudo-transient and higher order term relaxation, both of which aid in the robustness of the solution. I'll set the simulation to run 400 iterations and initialize the case. Now I can run the Fluent Solver by clicking Calculate, and this concludes part 1 of this demonstration.